Good afternoon, ladies and gentlemen. Today, I will introduce our work on AI-based antivirus using a deep learning system. My name is Wang Lei, and my English name is Thomas. I'm from company Baidu. And I assume that you have heard of deep learning and also the Android APK file. Okay, let's start with a story. 12 years ago, my first job was a virus analyst. That is really a boring job. Every day I got a lot of virus samples, and they are detected by our competitors, but we missed. So when I got the sample, I know it is the virus. What I need to do is just to decompile it with IDA Pro and scrolling the mouse to find the signature, and then copy and paste the signature by the sequence to a text file. So at that time, I had a dream that one day the computer in front of me can take replace of me to handle virus samples, so I can have time to have a talk on Black Hat. So nothing's come true. Yeah. Okay. But one thing I learned from that job is that experienced analyst can identify a virus variant at a glance. Take this example. This is a decompiled APK file. If the analyst sees code like this in the red rectangles, he can tell if it is a virus at once. He didn't read the code to understand the logic, but he has seen so many virus samples like this. For the analyst, a new virus variant is just like a new handwritten number 6. He has seen so many 6, so he can tell if this is a 6 at once. This is image recognition, which is one of the best applications of deep learning. So this is the first reason we want to use deep learning in antivirus. Another reason is the Android malware has been growing too fast, and the signature efficiency is declining even more faster. You see the left figure shows the total number of Android malware these years. It has reached 15 million. And you can see there is a leap this year, which is not a good sign. And the red figure shows the signature efficiency against Dojin. Dojin is a popular Android malware family, which has a lot of variants. You can see that in 2013, one signature can catch almost 30,000 Dojin samples. But in 2016, one signature can catch only 1,000 Dojin samples. And worst of all, I have no high counts for new virus variants. So no virus analyst, so I have to think of other ways, for example, AI-based antivirus that not heavily depend on manpower. This is the roadmap of our mobile antivirus engine. We started with signature-based rules, which like anyone else, and then we found many virus families have obvious behavior rules. Next, we develop opcode-based rules, which can match some opcode byte sequence and has some logic with it. And finally, we get to the AI-based deep learning system. Deep learning has two stages. One is training stage, the other is prediction stage. The input of training stage is training data size. In our system, it's 15 million Android APK files, including malware, PUA, and benign apps. The first and most important step in training stage is feature extraction. We have structural type features, statistical type features, and empirical type features. These features, some of the features has continuous value, and some others has 0, 1 values. The continuous value has very different range, and the distribution of the range is very uneven. So we need to do normalization, feature normalization, to make to align the data to a same range and make the distribution as even as possible. When we get the normalized data, we can input them into the deep neural network for training. And we train the data on PyDo platform. It's an open source deep learning platform. To improve the network structure, we add a residual layer. And we also use sparse autoencoder to get high quality and invariant features. And we will also discuss some configuration tunings. After training, we get models. We train the malware model and the POA model separately. With these models, we can do prediction, pick up an APK from testing data sets, extract its features, and normalize the features, and we input normalized data into the model to get a prediction result. And is it a malware, a POA, or benign app? The next three slides will be the focus of today's talk. So let's look at the first one, feature extraction. Deep learning system cannot accept an APK file as input. So we need to tell the system what should be looking for. That will be informative in making decision. This is feature extraction. We have structural features, statistical features, and empirical features. Structural features is mainly about the information of APK file structure. For example, the number of uses permissions in Android manifest file, the number of picture file in RES directory, the size of RES directory, the number of classes starts with L,com/, the number of classes starts with R/Java/, the number of fields with type boolean, the number of methods which has parameters greater than 20. You can see that the structure features is very intuitive and primitive. That's exactly what we want. Besides structural features, we also have knowledge-based features, such as the statistical features and empirical features. An example of statistical feature is the discriminative string in certificate file. We collect certificate files from all the samples from the training data sets, and then we count the string occurrence of each field. Then we found this string. Email address equals mgame@mobile.com. This string appears in malware. It's 52 times later appears in benign apps. So we use this string as a feature. Empirical features is mainly based on various analysts' experience. For example, RES directory in the APK file is designed to store resource files such as pictures and XML. But various analysts found that some malware sometimes put executable file into RES directory. So we use if RES directory has executable as a feature. Similarly, we have if access directory has APK file as a feature. Since deep learning system only accepts real number as input, so we need to convert all these features to real numbers. Some of the features can be converted to 0 or 1 value. For example, if RES directory has executable file, if it has, then the value is 1. If not, the value is 0. Some of the values can only be converted to a continuous value. continuous value has very different range. We can see that there is 7, and there is 7, and there is a median number in these features. So if this number input into the deep neural network directly, the strings with small values will soon be surprised, and the effect of small values features will be greatly reduced. So we need to align the data into same range, and besides that, the distribution of each range is not even. We need to make it as even as possible. This is a feature normalization. It is very important, and we have done a lot of work on it. Let's see some details. Ideally, feature data obeys Gaussian distribution. We can use the standard score normalization to align the data to a closed interval between -1 and 1. It's perfect, but the reality is much more complex. For example, the size of certificate file. This feature's distribution looks like this. A vertical line parallel with y-axis. Seen from this distribution, this is a very bad feature because it's not discriminative. The system cannot make decision depend on this feature. All the samples has the same value in this feature. So, however, when we double check the data, we found that this is actually a noisy problem. There are some very large values at the far end of x-axis. So we use cutting techniques to cut off the noisy data. Then this distribution transform to this one. It's amazing. A vertical line transformed to a multi-model distribution. This is much more better because it's much more discriminative than a vertical line. But this distribution can be further optimized because you can see there are 6 peaks in this distribution. It's not even. So we use cutting techniques again to cut it into 6 Gaussian-like distributions. And then we can use standard normalization to align the data to a closed interval between -1 and 1. Another example is the file numbers in APK file, in APK package. The file numbers in APK package. Its distribution looks like this. It's a long tail distribution. For this one, we can use Quantile Normalization, which is find quantiles that can divide the data evenly, and then align each division to close interval between -1 and 1. This is a key part of this training, of the training stage. You have to find appropriate algorithms based on your own data characteristics, and it's effective. Our system, the precision of our system has increased by 9% with this normalization. Okay, after we get normalized data, we can input them into the deep neural network training. This is our network. This is a typical feed-forward artificial neural network, which has a 1 input layer, 1 output layer, and 3 hidden layers. To improve the network structure, we also add a residual layer. The difference between residual layer and the common hidden layer is that common hidden layer only accepts inputs from previous layer, and but residual layer will receive inputs from not only previous layer, but also the layer before previous layer. It's called identity. identity has no weight parameter, or we can say the weight parameter of identity is always equals to 1. Now look at the input layer. We have 571 continuous features, and we have 664 01 features, totally 1,235 features. You may think 1,000 features is a little small for the deep learning, but I want to say it's good enough. We have spent a lot of effort to reduce the feature from 10,000 to 1,000, and more importantly, 1,000 feature can work on mobile phone. We will discuss the production deployment in the next slide. Okay, and now let's talk about the training process. We use sparse autoencoder to train this network first. Autoencoder is unsupervised learning algorithms that can find high quality and invariant features. It applies backpropagation and settings the target value to be equal to the inputs, like this schematic diagram shows. By placing some constraints on the network, for example, most neurons should be inactive, we get sparse autoencoder. Using autoencoder is the main difference between deep learning and SVM. Yes. After training with autoencoder, we train it with labeled data. Now let's look at some configurations of this neural network. We use tense and ReLU as hidden layer activation function. You can use sigmoid, but these two functions is faster than sigmoid. You use multi-class cross entropy as a cost function, and we use ADA data as a learning method, and we use softmax as a final layer activation function. Softmax can be used for a multi-classification problem, and the training passes is 20 to 30. 100 passes will cause overfitting. That's it. So when we got the models, after training, we can get the models. Then we can do the prediction. This is the production development of our system. We extract the features on the phone and then send the features to the cloud. We do prediction in the cloud, considering the performance, and then send the prediction result to the phone. The whole process only takes 140 milliseconds, and the traffic is 1 KB per APK. To evaluate the detection performance, let's check the ROC curve. This model is trained on July and test against the AV test samples on July. You can see that this model has very good detection because its recall is almost 96%, and for the positive rate is almost 0. Let's look at the model lifetime. This model is trained on January and test against the AV test samples on January, March, May, and July. We can see that the recall rate has dropped by 7.6 in 6 months. So see from these figures, we can know, although the model has very good detection performance, but it needs to continue the training with the labeled data. Otherwise, the recall will drop. Yes. Let's talk about the limitations. First, deep learning can't provide explanations for its detection results. Those SVM can do it, but deep learning can't. It is because there are too many parameters in the hidden layers. But it also has a benefit that attackers don't don't know which feature caused the detection for its malware either. And besides that, the features are mainly primitive information, such as the number of files in APK and the size of a directory. So it's more difficult to evade detection. Second, our system can't understand code meaning. It's learned in an image recognition way, so it don't even try to understand the code meaning. Third, it's built on static analysis and a lack of dynamic inspection. And last, it can't self-learning, need continued training with labeled data. We have seen it in last figures. And it also has advantages. For example, more difficult to evade, we have just discussed, and it has a fixed size model. The size of a traditional signature database grows with sample size linearly. But the deep learning model, the size of deep learning model is only related to the network structure. For our system, the model size is only 2 megabytes. Conclusion. Feature extraction is the key step. Virus analyst experience and autoencoder can help to find valuable features. And this system is designed to detect Android malware, but these methods can be used in detecting malware in other platforms. Last, our system learns in image recognition way. It's effective only in detecting malware variants. But if it can learn in a speech recognition way, maybe it can understand the code meaning and read the code logic to uncover a new malware family. And that might be what we are going to do next. Welcome to contact me for any reason, and welcome cooperation and partnership with us. Thank you all. Thank you.
Ladies and gentlemen, we have time for a few questions. If anyone has one, please just put your hand up. Microphone.
Hi, thanks for the talk. You mentioned that you need labeled input, right, for your training?
What input?
Labeled.
Labels, yes, labeled data.
Where did you get the labeled data from?
Oh, yes. I have a team focused on mobile antivirus, so we have a lot of crawlers and get samples. We also have sample exchange with other security companies.
Ah, okay. Yeah. Thanks.
Yes.
Else? Thank you, sir.
Hi, great talk. Why do you have to normalize the data before pumping it into the neural network? So why can't you just plug the numbers straight in rather than normalizing them?
Why normal? Sorry.
So why do you have to normalize the data before putting it into the neural network?
Oh, yeah. For two reasons. First reason is the data has a very different range. Some range from 10 to 100, and others range from 100 to billion. So if this data input into the neural network, some big values will surprise the effect of small values. The neuron, if neuron accepts a very big value, it will be I don't know how to say it, but it will stop accept the small values. So we need to align the data into a same value range. And the other reason is this is not enough because it is not if the data is not even. Look at the look at this vertical line. Then all the samples have same value. This feature is useless for the system because it can't make a decision by this feature. So we need to do to make it the distribution as even as possible. Yeah.
Hi, good talk. Can you mention something about false positive rates?
About what? Sorry.
False positive rates of detection.
Hot.
False positive.
Oh, sorry, what's that? Oh, false positive rate. Okay. You can see the raw curve shows a false positive rate. Yeah. The x-axis of a raw curve in the middle figure is the false positive rate. Our model has very good detection. The positive, yes. The first goal of this system is to control the false positive rate or the precision, because we want to use it to attend AV test, and it already attended AV test on January this year. For this comparative test, the false positive rate is very important for this comparative test, because if you have one false positive rate, you get punished very severely. So the first goal of this system is to control the precision or false positive rate. But I think the deep learning system, using deep learning to do antivirus, should not control the precision of false positive rate too much. It should let it go, and the recall is the most important point of this system. Yeah.
One more question? Thank you. Thanks.
Hi, thank you for the talk.
Thank you.
So, image recognizer neural networks have been this line of work of adversarial samples. And basically what people have showed is that you can do some specific changes in the input, very small, like say less than 1% of the features of the pixels, and cause the network to misclassify the input. So given that you follow a similar line of architecture, and here it's very important to correctly classify, have you looked into this area of like these algorithms causing misclassification, saying like changing one feature by a very small value, and this will cause the network to output a different value? So yeah, I was wondering if you are aware of this area and whether you are planning to test such algorithms against your system.
Sorry, I don't understand your question very clear. We can talk about after the talk.
So basically what's happening is that image recognition neural networks, there are this line of work that you can basically cause them to misclassify inputs. You have an input which is an elephant, and by changing 2 pixels, you cause the network to classify it as a carrot with very high precision, with a very high confidence. Sorry. So I was wondering whether you're aware of this, because you follow a similar architecture, whether you have tested any of these algorithms against, your system.
Yes, let's discuss it after talk.
Okay.
Face to face, yes.
Thank you, ladies and gentlemen. We're out of time. If we can thank Thomas.
Too long. Thank you. Thank you.